The Centennial Andrews expedition to the Gobi Desert is an experiment in using the latest field technology to enhance the exploration of geologic sites for their paleontological resources. Similar to the way Roy Chapman Andrews used new mass-produced automobiles to accelerate field methods in the early 1900s, today we are using the latest in drone-enabled survey systems to give field geologists and paleontologists an enhanced perspective of the landscapes and geologic environments that may harbor information about the evolution of dinosaurs. The flight platforms we are using are consumer-grade drones that are light and flexible, capable of being deployed in nearly any environment with minimal support infrastructure. Keeping to the theme established in the original expedition, we will be using the state-of-the-art in field vehicles, Infinity's latest SUV, to carry an international crew of scientists and adventurers across the most remote reaches of Mongolia. Our UAV-mounted multispectral and thermal infrared camera systems are modeled on the satellite instruments we have used extensively in orbit around Earth and Mars, where mineralogy and surface materials can be quantitatively determined based on spectral properties. What makes this approach so unique and ideal for dinosaur hunting in the Gobi is that we can collect the data at the ideal time and resolution to be able to pick out potential fossil exposures down to the multi-centimeter level, while still covering huge areas during the course of a day. The key to successful fossil prospecting is to identify the rock exposures where lithology, depositional environment, and sediment grain size are ideal for fossil preservation, but also where erosion is currently causing fossils to become exposed to the surface. Traditionally, this is accomplished with experienced field crews roaming an area looking for the right exposures that have yielded fossils in the past. The primary limit to these methods is the distance that a person can cover in a day over rough terrain where fossils may be difficult to identify visually. Remote sensing tools, such as multispectral imaging, can be tuned to be able to highlight the differences in mineralogy to interpret these exposures. Using data from the ASTER instrument currently in orbit, we can show these differences easily at the 15-meter scale. Too coarse for detailed work, the satellite imagery provides the generalized geologic maps that will guide targeted drone missions. The imagery shown here highlights the differences between clay minerals, sand, and dark, stable desert pavement surfaces, creating almost a colorized map of the geology. Switching to thermal infrared, we are able to use the temperature of the surface to show where differences in mechanical compositions can highlight dense blocky objects, such as large fossil dinosaur bones, against the finer grained matrix that contains them. Together, these tools do what a human surveyor does, identifies the exposures with the most potential, and identifies large fossils. But it does it in a consistent manner over an area that is much more than a person could possibly survey on foot. In the end, it still takes a person to be able to identify any signs of fossils, but in an environment where erosion is constantly destroying the evidence of prehistoric life, these tools give paleontologists an edge that never existed before.